I'll give you a brief introduction. Dave Wright is a finishing grad student at Oregon State, or has finished
3 weeks.
3 weeks. After which he'll take up a postdoc at Imperial College London, working with Andrea Mitridati on all sorts, but probably new physics signals and developing more powerful data analysis techniques for PTAs. And is one of the chief developers of PTArcade. So he's going to give us an overview of how that code works. So whenever you're ready, Dave, take it away, and let's give him a round of applause.
Thank you. I'm going to go ahead and start recording. So we're recording now, and I'll share this around later. So during the break, hopefully you had a chance to do a Git pull and a UV sync. I pushed my slides for today and the notebook that we're going to work through to the VIPER GitHub repo. It's under week 2, day 1, and then PTArcade. So I'll take a break when we get to the tutorial piece to help everybody get things installed. But the slides are there if you want to look at them on your screen. I am going to share screen here in just a second. Like Andrea said earlier, remote talks, are a little bit different and strange. Please yell out or put something in the chat or on Slack if you have any questions any way through. Stop me. I'm more than happy to answer questions during the talk. But the plan for today is to do about 15 to 20 minute intro to what PTArcade is. And then we have a notebook that's going to walk us through doing a search for a phase transition model. So the one you heard at the end of Andrea's talk, we are going to search for that model in some simulated data and see kind of how an end-to-end PTArcade run would work. Okay, so let me go ahead and share screen. Share. Desktop 1. All right, hopefully everyone can see that. Great. All right, so new physics searches with PTArcade, right? So let's start out. I know you guys have probably seen a lot of review and overview over the last few weeks, but just to kind of set the stage, where are we kind of with PTA science? So our latest results show that we are starting to see some evidence for there being a common correlated signal, right? With these Hellings and Downs correlations. And so we have some evidence of there being a background. And our next question becomes, we have some evidence. We think there's some kind of gravitational wave background. What's the source of that background? So in PTArcade, we are posing the question, could it be new physics, right? Could something outside of the standard model or some kind of cosmological model be the source of the GWB? And so I say new physics, what does that mean? And some of you may have heard me make this joke before, but there are these two books that have the sum total of human knowledge, what they teach you at Harvard Business School, what they don't teach you at Harvard Business School, right? And there's everything in here. That's kind of how I like to think about what's new physics, okay? So there's supermassive black hole binaries, and then there's not supermassive black hole binaries as sources of the GWB. The new physics lives in the not SMBHB part of that. So the sum total of these is all the sources we could consider. And today we're going to be thinking about things that are not astrophysical. All right. So in fact, we've already used PTArcade to do a large-scale search over non-supermassive black hole binary GWB models. Some of those models include inflation. You got to make a few modifications, though. Basic inflation isn't really going to produce the signal we're seeing in PTAs. Scalar-induced gravitational waves, these are primordial black holes and things like that you've heard from Andrea about. Phase transitions, so first-order cosmological phase transitions. This is what we're going to work on in about 15, 20 minutes if I keep time. That's what you heard in Andrea's talk. Topological defects, these are kind of consequences of phase transitions. Andrea made the analogy with bubbles and changing phases and like water and things like that. You could imagine that the topological defects are an analogy to that. If you had some water that's freezing and you get cracks in the ice, that crack is a topological defect. And these kinds of defects can produce gravitational waves. This is where cosmic strings and things like that come from. Fuzzy dark matter, since it's ultralight dark matter, Andrea talked about this too. And these have all been so far stochastic gravitational wave backgrounds, but we could also look at deterministic signals in PTAs, and one of those being dark matter substructures. So maybe you could find a primordial black hole floating around somewhere, and that shows up as a deterministic signal in our array instead of a stochastic background. If you haven't looked at the Nanograv New Physics paper, I'd encourage you to go take a look. We test all of these models in there. But the question is more than what fits. It's what fits the best. Supermassive black holes or new physics, or maybe a combination of both. Maybe there's an astrophysical background and a cosmological one layered on top. And in actuality, it's the other way around. We would treat the astrophysical background as a foreground, and then the cosmological signal really is a background. In fact, we've also done those searches using PTArcade. So here is a plot from the New Physics paper showing Bayes factors, which you've heard about in lectures this week. These are model comparison metrics that tell us how well one model fits the data compared to another. And so in the blue, we have just new physics by itself. In the red, we have new physics and an astrophysical signal layered on top of it. And the Bayes factor is with respect to just a pure power law expectation for an astrophysical background. There are a lot of models here. I won't read them all off. And if you go read the paper and you look at these figures in detail, the takeaway from this is not, oh, we found cosmic strings. The takeaway is that the data doesn't like a power law. The data wants something a little bit more advanced. And these new physics signals have that. In order to make these Bayes factors, we use something called product space sampling, which I'll say a bit more about in a second. But that's essentially a transdimensional thing where we can turn signals on and off, and we can count how many times a sampler stays in the on versus the off position and use that as a Bayes factor. And I think Tyson's giving y'all a lecture later this week on advanced sampling methods. You'll probably hear a little bit about transdimensional sampling then. All right, so now let's go into the actual signal you're going to be fitting. It's going to be a first order phase transition. I think you saw some of this earlier, but we're specifically going to be looking at gravitational waves sourced by bubble collisions from the phase transition. It takes a generic broken power law shape. This is what the S of X is there. And then there's a lot of pre-factors that handle amplitudes. In the notebook we're going to work through, I've given you those things, but we're going to code up the spectral shape here. Andrea's already told you what the parameters mean, so I won't go over that again just to save some time. And he already mentioned that this is near the QCD phase transition, so that's why PTAs care. The phase transition that could be in the nanohertz band is something that modifies the QCD phase transition. For the LISA folks, the electroweak phase transition, if it was first order, would fall directly in the LISA band. So that's an interesting thing for LISA as well. All right, on to more PTArcade. PTArcade is just at its basic level an easy to use Python program that lets you do new physics searches in PTA data. This grew out of the needs of the new physics group as we were coming up with these tons and tons of models to test in the data. We wanted a very simple thing we could just launch on a cluster, and people didn't need to know super detailed PTA data analysis. They could focus more on developing the models that we search for instead. So all you need to run a PTArcade analysis is some kind of Python file that in a functional form has down the spectrum of the model you're looking for, if it's a stochastic model, or if it's a deterministic one, a model that gives you the time series that should show up in your residuals. PTArcade is going to download and get all the data for you, so you don't have to supply data. It builds the full inference pipeline, it builds the likelihood, the sampler. It'll do the model comparison for you. It's also going to help you with analyzing the chains, making the publication quality plots. All the plots that are in the new physics paper were just made with PTArcade's defaults. And then finally, all of the configuration is done in configuration files instead of one-off scripts. So this makes it really reproducible. And when we were doing all of these different models across multiple different clusters over the world, I was running some analyses and I had someone else in Germany running the same models on a different cluster, right? We needed a way to really easily exchange our setups. And so everything's in config files. You can check them into version control and share them with people. Makes things really reproducible. So at a basic level, how does it work? PTArcade is meant to function as a command line tool. So you'll have a PTArcade command, an M flag, you pass in that model file that has the spectrum or the time series that you're going to search for. Then that config file, and then also we give you an N flag that lets you say what the chain number is, which helps with naming things if you're going to run multiple chains at once. But what it does is it's going to read in those config files. It's going to look at what mode you're running in. So PTArcade can connect to a lot of different likelihood codes. Keffel, Enterprise, we're working on Discovery as well, and maybe more in the future too. It's going to configure the right likelihood and sampler for those modes. It'll download the data. Then it's going to set up your sampler, run things, and give you the chains. All you have to supply is the inputs. It's going to give you some nice verbose outputs as it goes, but it's all pre-made. So here is a quick example of a model file. So this is for this spectral shape here at the top. And everything in PTArcade is going to be done in units of h squared omega, omega GW. And so what this is it is a it's the energy density in gravitational waves as a fraction with the closure density. So the closure density being the density the universe needs to achieve to be flat. So this is the kind of units we work with in PTArcade, and internally we'll convert them into the units that PTAs expect. So what you'll see first is we name the model. This just helps with the output directory so that you don't overwrite things later on. We say whether or not we want to superimpose the astrophysical background, and then we put down priors on the model parameters. So when you write this spectrum function here, this is going to be the spectral shape of what you're searching for. The first argument is going to be the frequency, and then the next will be any arguments besides frequency that your model needs. In the parameters dictionary, you'll need to put down the same names, and then you're going to use this prior helper from PTArcade. And this seems a little weird, but we made this because we interface with a lot of different codes, and we needed a way for our priors to work with multiple different codes. So like Enterprise has its own priors, whereas Discovery, we use some kind of probabilistic programming language, or we use priors that are built in there. And so we have this kind of higher level helper that'll dispatch to the right codes underneath. But the way it works is you say the name of the distribution and then the parameters that go to it. So here's a uniform, and today we're going to just use uniforms, and then the bounds, the lower and upper bounds, and our spectrum. That's it. And that's what you hand to PTArcade. It'll construct the right things in the likelihood. And again, the spectrum model is supposed to return the it's supposed to return the power in h squared omega GW, and we convert it underneath. This is nice because if you're looking up different models, new physics and cosmological models in the literature, you're 9 times out of 10 going to find them in these units anyways, and then we convert them. If you're doing a deterministic signal, instead of writing a spectrum function, you write signal, and then you take in arguments like the TOAs, the pulsar positions, things like that. And PTArcade will recognize that it is a deterministic signal, and it'll build the correct likelihood for that. Right now, this only works in Enterprise and Discovery, and we'll talk about why it doesn't work in the mode we're going to use today. But we're going to be working with a stochastic signal, so that's all right. In addition, we've added some things recently that allow you to put in custom priors, or you can specify whether your parameter is common to all pulsars or not. So this G parameter, for example, we say common is false. That means it's going to set a G for each of the pulsars. You'll notice we don't do any kind of intrinsic red noise or things in here. Whenever you specify which data set you're using, PTArcade will apply the noise models that were used for that data set. So that's all done automatically as well. Okay, so I'm going a little slow, so I'm going to go a bit faster. You can specify which data sets you'd like to use. Right now we have NG15. We have EPTA in here too, and I forgot to put that in here, NG12.5, IPTA. It'll go and download those from Zenodo, or you can give it your own data, which is what we're going to do today. The modes that we're going to mostly use are Keffel or Enterprise. Discovery is still in testing, but that is on Dev, and we're going to use Dev today. You can also tell it how many samples you want out of your sampler, where to save things, where to resume, things like how many frequencies to use, whether or not to use spatial correlations, and whether or not to do model comparison. All of these things are what's going to go into your config file. One thing we've added recently on Dev is some cosmological constraints. So you can say whether you'd like to apply additional constraints from Big Bang nucleosynthesis, this using the effective number of neutrino species, or some LVK bounds as well. These are going to just add factors to the likelihood that additionally bound by these extra things. We're not going to do that today. So if you don't have a closed form analytic spectrum, but you have some kind of tabulated data, some kind of simulations, we can handle that as well with PTArcade. We have a function called spec importer that'll read an H5 file, which we have instructions in the documentation about how to make. And then this will really quickly interpolate that tabulated data for you. We also have a lot of helpers when you're doing these new physics models. You need to use natural units. You need things like the energetic and entropic degrees of freedom. Things like that are all in there for you already. The other thing is if you're doing modified gravity searches and you have different ORFs, that's something that we're experimentally testing right now as well. All right, so the different backends, like I mentioned, we have Enterprise, Discovery, and Keffel. Enterprise is kind of the production level one, what you would expect. You can use PARS and TIMS. We can do model comparison. We can use stochastic or deterministic signals. Discovery is a lot faster, but it's still in testing. It's a little bit less flexible, but we're working on developing that. What we're going to use today is Keffel. So this is Williams code that is very, very fast. It works on pre-computed kernel density estimators of the free spectrum posteriors, and it's only going to work with stochastic signals, and it's not going to work with model selection, but that's okay, because that's what we're going to do today. And very briefly, what Keffel does, if you haven't seen this yet, Keffel is going to take a kernel density estimator on each of our free spectrum posteriors. So a free spectrum in PTA speak is just, what if we didn't assume a spectral shape, but we just looked at what is the what's the most agnostic thing we could recover at each of our frequency bins, and then we'll refit data to that. That's what we're going to do, and this allows us to write down the likelihood as a product over frequencies, where each of those frequencies data is represented by a kernel density estimator. Not super important to understand at a deep level, but that is what we're going to do today. So I'm going to skip over this because I'm going a little slow. After you have your posteriors, you can import the chains, those posteriors, and you can make plots. PTArcade has built-in plotting utilities. You can plot how your chains have converged, things like that. You can also plot these nice corner plots here on the right. This is from the new physics paper, and we're going to use this plot posteriors in our tutorial today. There is very extensive documentation on the GitHub pages here. I would recommend you take a look at those. That might be useful during our tutorial here in just a few minutes. We've put a lot of work into these, and there are examples and overviews, but also every single function has a doc string, and you can go read how everything should work. Okay, so wrapping up, and sorry I went a little bit fast, but I want to make sure we have time to go through the tutorial. What's going to be in the near future for this kind of stuff and for PTArcade? We want to kind of go beyond spectral characterization to differentiate between astrophysical and new physics things with anisotropy, for example. So going beyond just spectral characterization. We also plan on integrating some full SMBHB population models, so not just our power law, but something a little bit more advanced. And these limits from cosmology, LVK, the custom priors, all these new things are on dev, and we're testing them, and we're hoping to make a release soon. And finally, the kind of biggest change we hope to make in the near future is a larger refactor that's going to allow us to more easily integrate new tools. We have lots of new PTArcade tools floating around, things that are much faster, much more efficient, and we want to integrate those, but we need to do a little bit of refactoring to make those easier to integrate. Okay, so that is what I have for you as a warm up. I'm going to check the chat really quick and stop sharing and see if anybody's got any questions before we go on to the tutorial. Nope, well, we don't have many people in Zoom, so I'll just see if there's any questions from the audience. Any questions?
I don't think so, Dave. I think you're good to get on to the work tutorial.
Great. All right. So we will get on to the tutorial. I think I have about 30 minutes. Is that right, Steve?
Yeah, that's good.
Cool. All right. So if you go into your VIPER directory that you hopefully did a git pull and a UV sync, and you go into week 2, day 1, you're going to see a directory that I made a few hours ago. And I want you to open up the PTArcade tutorial notebook that's there. And if anybody's got any questions or things are stuck, I'm happy to help out.
Yeah, I'm going to stand up here and be your proxy in case anyone has any installation issues in the room, Dave.
Thanks. Yeah, I'll wait a few minutes to make sure everybody is set up, and then we'll get started.
Installation successes / woes. Any issues? Thumbs up. Good. Any thumbs down? Good. I know there were some issues with installation of various tutorials and packages last week. All good? Okay. I mean, it seems like it's going okay, Dave.
Oh, okay. So hopefully everybody's got this set up and ready to go. The way that I'm going to do this is I'm going to walk you through. Well, we're going to walk through the notebook together, but there are sections where I want you to fill it in, and I'd encourage you to work with a partner. And I'll give you some time, and then we'll come back and I'll write up the solution just to make sure we're all on the same page, and we'll keep moving forward. And as before, please yell, scream, interrupt me if you have any questions. Hopefully you can see my notebook here. I can make the text a bit bigger if that is useful and everyone can read. Hopefully you have it locally. All right, so let's get going. As I said at the end, we are going to work with this simulated data that I made. And I'm also going to upload all the notebooks and scripts that I use to simulate this data, run the free spectrum model, and create the couple KDEs if that's something you're interested in. I'll post those along with the solution notebook later today. Interesting to look at, but not necessary for this lecture. All right, so what we have is a free spectrum, which I've stored in this free spec directory. I've made those Keffel kernel density estimators for you. And this is what PTArcade would typically download automatically if you say you want to run something in Keffel mode. But I've made one. It's a common uncorrelated model, so no spatial correlations, just per speed when I ran this on my own. And it's going to have 14 frequency bins, and it's a 16-year data set based on the 15-year data, so 16.03 years of data. But now our question is, can the signal have come from a first-order phase transition? If it did, what kind of parameter constraints can we put on it? So what we're going to do is we are going to go through loading the data. We are going to write a PTArcade model file and a config file. We're going to run PTArcade from within the notebook, even though usually we run it from the command line. And then we are going to analyze the posteriors. So starting off, the first thing we want to do is I'm going to define some parameter names of the new physics model. This is not super necessary for typical searches, but because we're doing this interactive thing in plotting, I have these globals ready to go. We are going to then load in the frequencies corresponding to our Keffel KDEs, our free spectrum. And that's going to work. And it tells us we have 14 frequencies and the range of those frequencies. Okay. Now, the major step in defining a PTArcade inference run is building the model file. So as we said before, it's just an ordinary Python file. It's going to need two things at the basic level. This parameters dictionary, it has to be called parameters. We look for it whenever we set things up. It's going to contain the arguments to your spectrum function as keys. And then as values, it's going to be this prior helper where the string is the name of the distribution. And then the arguments are the bounds, or if it's a normal, it's the mean and the standard deviation. So we have a parameters dictionary. And then we have, for a stochastic model, the spectrum function. And it's going to take frequency as the first argument, and then whatever the parameters are corresponding to the model. And again, those names have to match the keys in the parameters dictionary. This spectrum function is supposed to return h squared omega GW. So this is the PSD prior in cosmology units, essentially. All right. There's optional things, like we said earlier. There is the name you can specify that's going to tell you what the output directory is going to be named, and then also the option to add on an astrophysical signal, which we're not going to do today. Everything else in that file is just Python, so you can do whatever you'd like. You can define helper functions, you can load your own data, whatever you need. The two things that are really necessary are the parameters dictionary and the spectrum function. PTArcade is going to look for those. So our signal, which we talked about in the warm-up, is going to be this broken power law, this spectral shape given by the following S of x, so on and so forth. The way to reason about this is that below this turnover, it's a broken power law, right, with this turnover. Below it, it goes as f to the a. Above it, it goes as f to the negative b. And c is going to tell you how sharp the turnover is. It's going to be a function of the frequency divided by the peak frequency. So this is just a scaled frequency. And that's something that I give to you in the cells down below. All right. So here are the priors that we're going to use. For each of the parameters, these are working in log space, but the priors are as follows. Log 10 alpha is -2 to 1. It's uniform. T stars -4 to 4, so on and so forth. These are going to be what you use in the next cell to write down your priors in that parameter dictionary. You're going to go back here and you're going to use these bounds and a uniform parameter. All right, now that's going to bring us to our first to-do. I have this cell here that's using this cell magic write file. It's going to write ptbubble-model.py when you run the cell. And I have commented here to-dos, and I want you to fill in each of the to-dos. So you're going to name the model. You're going to say whether or not to do SMBHBs. Don't do it, right? We already said not to. You're going to fill in this parameters dictionary with the right parameter names and the priors. Then you're going to go onto this spectral shape, this S of x, and you're going to implement it based off of what I wrote up here, or from the slides, if you want to look at the slides. So this S of x, where x is f over f peak. And then I've given you a lot of things down below. One thing else you have to do is convert these to linear space because they're in log space. But I gave you a lot of the nitty-gritty, tedious physics things about converting units and degrees of freedom and things like that. So I have commented out here what's given. And then finally, the last thing you'll do is you're going to put it all together. So the return should be this return here multiplied by S of x. And so you're going to do that, and then we're going to come back together, touch base, and we'll make sure everybody has a working model file. But just to reiterate, I have commented to-dos here, just Control F for to-do, fill in each of these to-dos. I think this will take us maybe like 10-ish minutes, and I will check in with you guys intermittently to see how things are going. I just got a notification that Zoom is going to kick me off of the meeting in 10 minutes. I don't know if anyone else saw that. I'm going to take this time to shut down and restart while you guys are finishing this up, just so that we don't interrupt what we're trying to work through. So I'll be back at the same link in just a minute. I am back to recording. Okay. So let's share again. Let's do desktop 2. All right, so hopefully everyone is making good progress. Has anybody gotten to finishing their model spectrum? So finishing this spectral shape. Right. Is anybody stuck on, for example, defining the parameters dictionary? Is there anything that I could help you with? Okay. So I tell you what, I will start working from the top, and we'll work through this together. All right. So the first thing I'm doing is defining the name. Then I'm going to say I don't want SMBHVs. Now for my parameters. Is that better? So I'm just going through and defining each of the parameters that shows up in the spectrum model. So first log 10 alpha, then T star, then HR.
David, can you hear me?
Yeah. What's up? All right. So that is our prior dictionary. Hopefully that is the prior dictionary that you all coded up. Does that seem right? Anybody have any questions about the prior dictionary that I coded up? It's just what's in this table translated into a dictionary. Okay. I'm going to go to the next piece, which is our spectral shape. And so this is going to be A plus B, B times X. All right. And we've got that right exponent in there. Let's plus A times X, B divided by C times C. So this is just copied off of here. A plus B raised to the C, A plus B raised to the C, and then all in the denominator, B to the B times X to the minus AC, B times X to the minus AC plus A times X to the B over C, and then the whole thing raised to the C. And that should be, let's do that. There we go. All right, so that is our spectral shape from earlier. Now we're going to convert to linear parameters where we are taking in log. So we're going to raise all right. Does that seem okay? Good. So we typically will work in log space for things that have very large dynamic ranges. And then we'll convert to linear space when we feed it into our models. That's a common thing you'll see in a lot of the models that we built. Okay, now this is all of the annoying nitty-gritty prefactors, normalizations, things like that. The next thing we have is to put all of it together. So we're going to take all of the physics pieces that are here and multiply them with our spectral shape. That's going to give us our final return value. So here is what we're going to do. We're going to do 1 divided by the norm times, here, I'll tell you what we'll do. We'll do return equals, sorry, ret equals, all right, and then we'll do 1 divided by norm times, this is going to be aux dot h squared, so this is the reduced Hubble constant, times the dilation factor, times delta, times h beta raised to the q, times kappa alpha, 1 plus alpha e. Now, finally, times our s that we wrote earlier, evaluated at f divided by f naught, so that's our x, a, b, and c. So this is just translated what's here into the final return down below. This is in units of h squared omega GW. That's why you get this aux.h squared there. And aux is just model utils from PTArcade. That's a historical thing. We got used to calling it aux when we imported it. But I've seen people call it, MU model utils. Anyways, oh, turn red. All right, so I ran this cell, which is going to give me here a PT bubble model, right? So this is just exactly what was in that cell, written to a file. The next thing to do is just quickly check our model, make sure what we wrote makes sense, right? And to do that, what we're going to do is use some parameters and plot the spectrum and see what we get out. So we'll run the next cell. And there we go. So this looks like it makes sense to me. We see that as our T star gets larger, so that's going, as the T star gets larger, things move to the left, to the right, sorry, and vice versa. So something that happened earlier, so at higher time, the peak is going to be later. That's what this is showing. So that looks good. This makes sense. Our units are, 10 to the minus 30. So everything is making sense so far. Great. So we have our model file now. Now what we need is our config file. There is a default one that ships with PTArcade. So this cell here is just going to show you what's in there. We're going to load it and print it. You'll see in here, the NG15 is the default. We have no model selection by default. The chains, things like this, how many samples, how many intrinsic red noise components, all these things are by default written for you, and you don't have to change them if you're okay with the defaults. When you make your own config file, anything that you leave out, it will just use the defaults instead. So what we're going to do is we're going to change the things that we need to change in order to do our Keffel run, because Keffel is going to be quick. And on our laptops, we don't want to wait 3 hours. We want to do it in 3 minutes. So we're going to change 3 things. The first is PTA data. we are going to make a dictionary instead of giving a string. So our dictionary is going to contain the path to the data. It's going to tell us which noise files to use, things like that. And in this case, because we're using KDEs, we don't need those noise files. We just need to tell it where the KDEs are. We're going to tell it where our output directory should be. And then we're going to tell it how many samples we want. And in our case, we want just to do 1,000,000 samples, just to keep it quick. Now, for sake of time, I am going to show you what we'll put in here. So to start out with, we are going to do PTA data. And we're going to do PSR's data. And our FreeSpec directory is right here, kefl FreeSpec. This contains all the kefl files. So we're going to do kefl FreeSpec. Now, remember, we don't need the noise data when we're using these KDEs. You would need them if you're loading pars and tems or pickled pulsar objects. And we don't need any empirical distributions either. So we are going to set those to none. Now, our mode is going to be kefl mode. So this will be nice and quick. And the other defaults, other than I'm going to change the output directory to be equal to PTArcade chains. And in samples, we're going to make 1,000,000. Everything else is going to be fine. So the defaults will leave. Everything there is okay. We're not doing model selection. Things like that are okay. So I'm going to run this. That's going to write my config file. If I open that, you'll see what's in here is exactly what was in the cell. So where our data is, what mode we're using, where to store the chains, and then how many samples we're going to take. All right. So now we have both files that we need. We have our model file and our config file. And we are going to run PTArcade. As I showed you earlier, we're going to say PTArcade-m, and then the config with -c, and then we'll just name it chain 0. Now in Jupyter, you can do a exclamation point, and this just runs a shell command, and that's what we're going to do. But if you'd rather run it in a terminal, that's fine. It'll give you the same answer. So let's run this. We should be getting some verbose output here in a minute. Here we go. So it tells me the name of my machine. If I had installed this high CPU thing, it would tell me cores, things like that. This is useful when you're sharing with collaborators and you want to know what your chainsaw ran on, things like that. So you're going to see a live update here at the bottom as the sampler runs. This should take about 3-ish minutes. While this is running, are there any questions? Anything that I could review really quickly from the previous cells? You're only getting the red line in the log T plot. Okay. That's probably because something happened with your for loop, because the different lines come from this for loop. All right. Anybody having issues with this running? Is it running okay on people's computers? About this. And I will upload the solutions today if people. All right, I'm going to leave the right side for people to look at, and we're going to scroll down. No, h squared is not Planck's constant. It is the reduced Hubble constant. So that is the Hubble constant divided by 100 kilometers second per megaparsec. It's just a scaling of the Hubble constant that makes it dimensionless. It's going to be 0.67.
Oh, no.
All right, so looks like my chains have finished. How are we doing in the room? Are things still running? Well, for sake of time and to not cut into you to your lunch, I'm going to just show you the results using my chains. And then when I send out the solutions later, hopefully you can go through and finish if that's something that you'd like to do. All right, so now we have outputs in the output directory we wrote down, the name of the model, and the number of the chain. So again, the number is useful if you're launching this on a cluster, right? You can imagine putting this into like a Slurm script and running 100 chains, and then each one of them gets their own directory so they don't overwrite each other. That's the kind of the goal behind it. So we have this directory now that has all these outputs. A lot of them we don't really care about for the purpose of analyzing the posteriors. They contain a lot of things about the sampler setup. The ones we really care about are the one that say chain number and what is going on here? I did an underscore, didn't I? Sorry about that. I put an underscore in there. So the ones we really care about are the chains, underscore number, that has all the samples, and then pars, which gives us the parameters that were sampled and where they appear in the chain. So I just printed out what's in that directory and then what's inside of that pars.txt file. So let's go ahead and inspect those results. We are going to import from PTArcade some chain utilities and plotting utilities. We're going to use this import chains function, and I'm going to change this because I did an underscore. And we're going to burn, so we're going to remove the first quarter of samples. And that's going to return to us the chain as a NumPy array, and then the parameters as a list of strings. Print this out. All right. And so what we have is 75,000 samples. It's already thinned by a factor of 10. And then the columns are going to be the parameters that we searched for, and then the posterior probability, the likelihood, the acceptance rate of the sampler, and then this in-par all is for product space sampling, which we didn't do, but the sampler always kind of puts it in there. So we just ignore that. So let's use our first plotting utility, which is plot chains. This is going to show us how the sampler kind of walked around as it sampled our posterior. Hopefully it looks like a fuzzy caterpillar and not like a staircase. That looks pretty fuzzy caterpillar to me. And we see down here at the right, the acceptance rates going up. So that's good as well. This is a good test to do to make sure your sampler isn't stuck somewhere. If we had to run multiple chains, we would really want to test the convergence statistics as well, but we're not going to do that right now. But this looks good. This means our model most likely didn't get stuck somewhere. So The next thing we'll do is actually plot the posteriors. So the first thing I do down here is I make labels, and these can be whatever you want. Here I'm making labels using some LaTeX, and it's going to give me nice rendering of each of the parameters we searched for. Then we use this plot posteriors function that takes in the chains, the parameters, what the labels are going to be, which parameters you want to plot, and other configuration utilities. The docstring is very verbose. There's a lot of other options. So we take in lists of things because we can do multiple chains at once. In this case, it's just one. So it looks a little bit weird that it's a list, but you can put in multiple chains at once if you want to overplot things. For anybody that's done cosmology work in the past, they really like getDist, and that's what our plotting utilities are built on, is getDist. This is going to plot our posteriors. It shouldn't take too long. Here we go. So here are our posteriors. These look pretty well converged. I don't see any weird bimodalities. But what we want to do now is we want to see if we could recover what was injected, right? So let's go on to the next part here. What we're going to do in this cell is we are going to overplot the prediction of our model onto the data. This is called a posterior predictive plot. We are just saying our model wants these parameters. What kind of data would we predict given those parameters? So we'll plot this. This is going to use LaForge, which if you haven't used LaForge yet, it's what we use to store chains and make plots and things like that in Nanograv. And it's going to overplot the predictions of our model in the right units. So there's some unit conversion that goes on in there. And this looks pretty good. Okay, so these are our KDEs, our violins, right? And the orange is the median fit and the 68% region, right? So this looks like it's fitting the data pretty well. So that's a good check. I had a slide in here to add in the injection parameters. Let me quickly do that, and then I will take some questions. And you won't have this, so sorry about that. This just didn't get copied from the solution notebook over to the student version, and that was my mistake. But here we go. We're going to load that in. Make a new cell. And here we go. Okay. This is going to actually overplot the injection, and we'll see what we recover. And truths was okay. This is the danger of doing things live, and I'll quickly go get this. Sorry about that. If all's well, we should recover things within the 1 sigma region. So this is, well, 1 sigma. These are the 68% highest posterior density intervals in the dark blue. And you can see that our injected parameters, for the most part, are lying within those. So this is a good check that we're actually recovering what we've injected. And Kat asks, to repeat what the dictionary and PTA data should be for the custom config? Yeah. So let me leave this up and I'll scroll back. So usually in your config, all you have to do is specify what PTA data you want to use, and then the path to the noise files, and maybe what the empirical distributions are. If you're using custom data, if you're using data that we've already provided, you just have to give a string instead of a dictionary. So if you were using the given data, you would say PTA data equals NG15. And it's going to go do all of this for you, and you don't need to do any of this. But in our case, because we're using custom data, because I made simulated data, we have to give it a dictionary. And we tell it where the data is. And because we're using Keffel, I give it the directory to where the Keffel KDEs are. And because the Keffel KDEs are already marginalized over all the intrinsic red noise and things like that, we don't need to tell it any noise parameters. So we don't need to give it any like white noise dictionaries for the pulsars. So I leave that as none. And then empirical distributions, these are what the sampler uses to make jumps, but we don't need to give it any of those because it's a simple model. So I leave that as none as well. So the only thing that you need for a custom Keffel run is to give it the directory that contains all of those KDEs. Any other questions about what we went through? So just as a reminder, what we did, I have some simulated data here that's got a phase transition in it. We set up a PTArcade model using the model file and the config file. We wrote those to disk. We ran PTArcade as a command line utility. And then we used some of the chain importing and plotting utilities to inspect the convergence of our chains and then plot the posteriors. This mimics pretty closely what you would do with a real PTArcade analysis. Most of the work is writing the model file. And I think that is, what we saw today. But that really is most of the work, is writing down the model file and making sure you have all the right normalization factors, things like that. In fact, in the 15-year, we had a little bug with this exact model where we got the normalization factor a bit wrong. So that is where most of your work goes into when you're doing these kinds of things, is figuring out what the model is that you're writing. And then PTArcade is supposed to handle all the other pieces for you so that you can spend all of your time working on the models themselves.
Dave, can you hear us?
Yeah, I can hear you.
Okay, great. On the Slack, if you've got access to it, there's a couple of questions that have been put there.
I answered a bunch as we went. Let me see if I missed some.
Okay, I could be wrong. But does anyone have any specific questions they want Dave to go over now, or is it a bit more convenient to put questions in the Slack for then Dave to answer? Do you think? Probably Slack. Dave, what we might do instead of the specific questions, if it's okay, do you mind if they just chuck some questions if they have any directly into the Slack? And then if you're able to, would you be able to answer them as we go?
Yeah, that works.
Awesome. Okay. Have you got anything else to show today at the moment? So did you get that one?
Sorry, I didn't hear you. What did you say?
Do you have anything else to show today, or is that
Nope. This is what I have for you all.
Beautiful. Well, thank you so much. It's a really great tutorial. We might leave it there, but yeah, if you don't mind answering any questions that come up on the Slack, that would be awesome.
Yeah, I will keep a lookout.
Awesome. Great. Everyone, thank Dave. Yeah.
Thanks, guys.
You're getting claps. I don't know if that comes through the album.
Appreciate it.
Cool. All right.